The second thing we discussed on the 19th was Spectral Doppler. I'm just going to quickly go through this. We discussed velocity scale on a machine, the sample volume size that we can change, spectral Doppler gain, pulse wave Doppler, high PRF Doppler, and CW Doppler and TDI, tissue Doppler imaging. The Doppler velocity scale, the definition of that is setting that allows the spectral Doppler tracing to be displayed as large as possible without aliasing. And the effect on our images flow towards transducer is above our baseline, which we can change the baseline. Flow away is below our baseline, and we can adjust to help eliminate aliasing, adjust our baseline, that is. Pulse wave Doppler on our LVOT is displayed here. Basically, we're sampling red blood cells and frequencies at a particular depth according to our stroke volume placement. The Doppler scale on the right, you can see on the screen over there, you can see the baseline here. You can see flow is going away from our transducer, so it's going out. Looks like it's going out here through the left ventricular outflow tract. That's what it says down here. It tells our values down here. Here's our baseline. Here's what's happening with our pulse wave Doppler. That gives us a bunch of stuff here. I can't see it very well from here, but basically this gives us all the information we need to know of the depth, the stroke volume size. Looks like it's at about 4 millimeters. Our wall filters are set at 150 hertz, and looks like we're imaging at 2.9 megahertz, and our gain is at 50%. This tells velocity through our LVOT. This is our all blood. This is our spectral Doppler right here, and our velocity max. And it gives us gradients, our velocity mean, it gives us a max and mean gradient, and it gives us our velocity time integral. And that's this dotted line measuring that outline of blood right there. See that dotted line? We can also adjust our sweep speed, define that by a setting allowing for adjustment of how fast our Doppler moves across the screen, so to speak. And the default on our machines is typically 50 to 75, typically 75 millimeters per second. And you can adjust that according to heart rate. If the heart rate's fast, you want to probably try to slow that down, and so on and so forth. The effect on our images: slower, more waveforms to evaluate; faster, less waveforms to evaluate. It may help with measuring in certain situations. And here we are showing a very fast waveform and a much slower waveform through our Doppler window. You can see this is Doppler, and this is boom, boom, boom. And here we have boom, 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 boom. So our sweep speed is much faster here than it is here. Our sample volume, the definition of that would be a setting used to decrease spectral broadening, where that's basically noise within our spectral Doppler window, in order to display the clearest Doppler window. And the effect on our images, if set too large, the Doppler signal may be noisy, picking up too much blood flow, making it difficult to distinguish laminar versus turbulent flow. We use our sample volume. We do that by setting our sample gate, if you will, at a defined location, and all the blood within that should be traveling at the same speed, our gate. Our sample volume, all lines represent blood flow. All the lines within this Doppler window, if set properly, you'll have a spectral window and laminar flow. This would be the proper sample volume size. Here, the sample volume, you can see this right here, probably be a little bit too big. We got a little bit of spectral broadening going on here. We just want to be careful where we place that. This would be an aortic valve. You can tell that because of the close and click, and probably a mechanical aortic valve. If our spectral gate is too wide, wider range of velocities equals the appearance of turbulence and spectral broadening, and that's what that there is demonstrating there. And here's another too wide of a sample volume gate with a lot of spectral broadening. This should be much cleaner and clearer than this. This should show this coming all the way down and so on and so forth. This is just all kind of grayed in, not showing a real clean signal for whatever they're measuring there. Probably a carotid or something. Okay, spectral Doppler gain. We have a gain button for our Doppler, spectral Doppler, and color Doppler. This is for spectral. Setting used to adjust the overall brightness of our spectral signal. The effect on the image is adjusted to detect the clearest signal, demonstrating full spectrum velocities with many shades of gray without missing important low amplitude information, which would happen if we undergained or obscured the true envelope with excessive noise, and that would happen if we overgained. We want to measure the modal velocity, that is the densest portion of the signal. That's what we're trying to measure. And here we can see where we have undergained, kind of increasing our gain a little bit here. And we can see this isn't a bad window here. This is probably pretty good spectral. Here, let's just kind of overgain. See how this gain is filling in the image here. The gain is too high here. Our Doppler baseline. That's our setting to move and adjust the baseline to optimally display the flow of interest. Here's our baseline right here, and we can move our baseline up or down. And you can see right here, this upper portion right here is showing aliasing. And we're going to talk about that in just a second. We talked about that in class. For this Doppler baseline, in order to get rid of this aliasing, we take this baseline and move it up. And that would bring in the true velocity signal down here, the peak velocity, and get rid of this aliasing signal up here. Aliasing only happens with pulse wave Doppler, and that's what we're talking about right now. So our transducer emits ultrasound pulses, which are sent to a user depth, defined depth, I should say, and we call it the sample gate or sample volume. The machine listens and waits for reflected frequencies of red blood cells. The Doppler frequency, which is audible because we can hear the blood flow, that has to be in the audible range, less than 20,000 hertz, rides on the transmitted frequency, and that's kind of I'll explain that in a minute. The Doppler shift then is calculated by the machine using a process called demodulation. It's basically going to extract that Doppler information from the Doppler signals, this Doppler sound from the wave, from the returning wave. So the Doppler shift is extracted. The transducer sends, say, at 5 megahertz, kind of high for, this is an example, high for cardiac, and reflects off red blood cells in the LVOT, for example. The reflected received signal, say, is 5,003,000 hertz, 5 million hertz. So if it's 5,003,000 hertz, that means we've hit a positive Doppler shift. The blood must be coming towards us because our frequency is higher coming back to the transducer than it was leaving. So the Doppler shift, frequency change, is 5 million hertz minus 3,000. You get 3,000 hertz. This is the Doppler equation. You're not going to have to know this Doppler equation for test purposes, but as I explained in class, you're going to have to understand what the Doppler equation is and how to use it to your advantage on the test, how it's used in Doppler acquisition, if you will. Pulse wave Doppler, the advantage is it has range resolution, meaning we can look at a specific velocity at a specific place and time. We're able to resolve velocities at a certain location. The disadvantage is that it can be ambiguous. So aliasing can happen, exceeding our Nyquist limit. Detected Doppler shift frequency, when that happens, is greater than 1/2 of our pulse repetition frequency. We're going to just quickly try to aliasing occurs when the detected Doppler shift frequency is greater than 1/2 of our pulse repetition frequency. Our pulse repetition frequency is determined primarily by Doppler velocity scale. We can adjust this and is limited by the maximum imaging depth. So in order to get rid of aliasing, we adjust our baseline, maximize our scale, and that of course will increase our pulse repetition frequency, Nyquist limit. So to adjust for aliasing, we adjust our baseline, maximize our Doppler scale, as I said, increases our pulse repetition frequency, therefore our Nyquist limit. If aliasing cannot be eliminated in normal pulse wave mode by maximizing the scale, let me try some called high pulse repetition frequency Doppler, which just basically increases the number of active sample volumes. But I want to explain real quick. We did this in class, and we explained it a little better in class, but the concept of aliasing. Basically, we need to sample our Doppler signal at least 3 times, 2.5 times, at least 3 times per wave. If we don't do that, if we don't sample at least 3 times per wave, then we can't tell what direction our Doppler is going in. So, for example, here we're sampling this wave here as many times as we need to correctly identify this wave. This is what this wave looks like. Here's where we're sampling it. Okay. Over here, this wave is it's going too fast, and therefore we can't sample it. So it's exceeded our pulse repetition frequency, or half our Nyquist limit, which is 1/2 the pulse repetition frequency. And you can see here we can't sample this wave. We need to sample it here, 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 and here in order to see the wave pattern that's coming back to our transducer, right? Well, we're only able to sample this wave here, so we're saying this wave looks like this, and it actually looks like this right here. So if we can't sample it, we can't see it, then therefore we don't know which direction this wave is going and what happens on our screen. And this is a slide that shows us a little more about the Doppler shift and how we get that, and how aliasing can happen if we're not sampling our wave at least 2.5, 3 times per PRP. Anyway, I explained this in class, and those people need to know. I'll explain it more in the next class. I want to continue on with this here. This shows the concept of aliasing. This is our mitral wave inflow right here, our E and A wave, and you can see this is mitral regurgitation signal right here. We're pulse waving right here, but we're unable to tell the direction of that regurgitation using pulse wave Doppler because it just goes this way and that way. It's just wrapping around, and we can't determine the direction of the flow. High pulse repetition frequency uses multiple sample volumes, increases maximal detectable velocity. It basically increases our Nyquist limit by a factor of 2, and so on and so forth. I'm not going to spend a lot of time on this, but multiple successive pulses are sent, so it's just increasing our PRF by a factor of 2. And if aliasing can't be eliminated in normal pulse wave mode by maximizing the scale, then we got to go to HPRF, is what I just said. Okay, wall filters. Talking Doppler wall filters. There are different types of wall filters. Talking Doppler wall filters right now. So this setting allows for removal of high intensity but low velocity signals. Basically, the signals we get from the heart that the heart walls are making. Those heart wall signals are intense, but they're low velocity. They're not like Doppler. So we don't want those in our Doppler signal. So these wall filters are able to filter out those high intensity signals. It should be set to allow unambiguous display of beginning and end of our Doppler signal. Example, how a wall filter works. If you set your wall filters, your Doppler wall filter at 200 Hertz, 200 Hertz and above, signals at 200 Hertz and above are allowed through that filter. Anything below this is blocked by the filter, and has a demonstration of that. Spectral wall filters. See here, your wall filters set at 50 Hertz, 75, and looks like 550 Hertz. And I want to keep an eye on the baseline. Okay, down here. And you can see there's a little signal, they call it a wall thump. And you can see this thump coming in here causing this signal enhancement down here. If you go right on the baseline. Well, if you set your wall filters to 75 Hertz, that wall thump is no longer there. See it right here, just barely see it in there. However, if you set your wall filters too high at 550 Hertz, you basically lose everything on that baseline. It's screening that anything below that out. So you want to properly set your wall filters. Okay, so you can see all of your Doppler signal. CW Doppler, not so much to say here about this. Continuously emitting pulses and receiving reflected frequencies. There's no waiting time, no Nyquist limit, accurate measurement of high velocities. We use this all the time in echo, of course. And we can't. The limitation is we can't, like pulse wave Doppler, we can't sample at a certain spot of blood velocity within the heart. So when we turn on continuous wave Doppler, we have two dedicated crystals, one for transmitting and one for receiving, receives a continuous signal along the entire length of the beam, not at a specific location like pulse wave Doppler at our sample volume or sample gate. The disadvantage, don't know where the signal comes from. It's coming from all the way through the heart. Advantage, can measure very high Doppler shift velocities, most useful when trying to discern maximum velocity in a certain path. We use this, of course, in AS and every other thing. It has a CW signal through the tricuspid valve. And you can see here they've measured right here. Looks like a good blood flow envelope here. All these Doppler velocities are in there. When you put that right here, we use the Bernoulli equation, 4 times velocity squared. And you can see here that that comes out to 36 millimeters of mercury after the velocity is taken into consideration here. Okay, tissue Doppler. This is a technique used to measure the Doppler frequency shift of the actual muscle of the heart, the myocardium. And we do that at the annuli of the mitral valve and tricuspid valve. We demonstrated this in class. Conventional PW Doppler assesses blood flow. Therefore, it's high velocity and low amplitude. Tissue Doppler imaging assesses muscle movement. Much higher amplitude, much lower velocity. You can see here our velocity 20 centimeters per second, whereas in our scale in Doppler 200 or more. And when we're using this, the machine automatically sets the presets to adjust for a larger stroke volume, lower velocity scale, filters set high for amplitude. So the machine does the settings for us. And we do have some degree to be able to change this. For the most part, the machine adjusts this for us. And here's an example of tissue Doppler imaging. This is our left ventricle up here. We've turned on our TDI. Anything that's contracting and moving towards our transducer is red. Anything that's relaxing is blue. Similar as in blood. You can see here red towards blue away. You can see the scale here, where our scale in Doppler is at somewhere around 60 centimeters per second. Our scale here is 15 centimeters per second. That's because we're measuring the actual movement of the base of this heart, the tissue itself. Oops, sorry about that. As opposed to the blood velocity. Blood is very high velocity, tissue is very low velocity but high amplitude. Blood is very high velocity but low amplitude. And here's where we're measuring. We're measuring the movement of this myocardium. And we've marked out an E and an A. That's our E wave and A wave. We talked a little bit about that in class. Okay, that's it. Thank you.